Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
So I have a picture on the screen. This is of Mount Pinatubo. This is not the cataclysmic eruption. This is a picture taken 3 days before the June 15th, 1990 eruption of Pinatubo, and I'll come back and I'll talk about this, but all I want to focus on now is that everybody has an image in your mind when I say volcanic eruption. You might think of Hawaii, or you might think of something like Pinatubo shown here. But nonetheless, what I want you to think of is that all of that ash that you see, that looks like the ash in your fireplace, that volcanic ash is mass, it's stuff. And that stuff used to be in the earth, and by some set of natural processes, that stuff that was in the earth has now been burped out. And so that's essentially a burping process where all of that mass, all of that stuff is now expelled. In this case, a lot of it went into the atmosphere, and I'll touch back on that in a few minutes. The photograph on the right-hand side here is of Yosemite Valley and Yosemite National Park in the Sierra Nevada mountains, one of my favorite places. And it's the only place my kids who are in the front row have ever camped where the temperature got into the 20s in the summer. What you're looking at is granite. How many people in here, by show of hands, have granite countertops? Same type of granite countertops in your kitchen comprise most of the rocks in Yosemite National Park. The granite rocks that you see here in Yosemite National Park, they formed or they solidified from the same magmas at which erupted at Pinatubo, but they formed at about 6 to 10 miles beneath the surface. And over the last 100 million years, all of the volcanic cover that was on top of them has all been eroded away. And owing to forces that we call plate tectonics that move things around on the surface of the earth, those granites have now been uplifted and exposed, and we can put our hands on and we can study them. I like to study what's in between those two end members. We've got volcanic eruptions, we've got these big bathtubs of magma that sit some miles beneath the volcanoes, and in between those two, we find ore deposits. That is a porphyry ore deposit that contains North America's largest concentration of copper, one of North America's largest concentrations of gold, one of North America's largest concentrations of molybdenum, and a significant quantity of silver. All metals that everybody uses on a daily basis. And you can think of these like a sponge, the ore deposits. We've got magma chambers, we've got volcanoes. If we think we know that the volcanoes, that magma originated from something like Yosemite at 6 miles depth, what I want to understand is as that magma goes from that source, that bathtub reservoir up towards the surface, what processes all of a sudden during that continuum take metals like gold and copper and silver and molybdenum and platinum and suck them into this really small area of the Earth's crust, much like a sponge. This is what it looks like quite often over the past 30 years on the southern flank of Kilauea on the big island of Hawaii. You can go and you can stand there. As part of my job, I was forced to have to go here about 7 years ago, and I had to stand there and take a video, and I'm about 15 feet from that lava flow. Okay, so if you like cooking Thanksgiving turkey, you cook a turkey at what, 400 degrees, 350? That lava is about 1,200 degrees Celsius or 2,000 degrees Fahrenheit. Okay? I will point out that as I was there, some characters that could probably be on one of Ryan Seacrest's shows asked, do you think it would burn paper? And they quickly found out the answer was yes. But I love experiments, and so I was applauding that they were doing that. Okay? I want you to keep this in mind, all right? Look at that lava. Look at how slowly it flows. It's oozing. It's almost like you imagine Earth is taking a tube of toothpaste and really slowly just squeezing out that toothpaste. Okay? It's not dangerous in the sense that it's not going to come up and grab you. It's not going to splatter at you. You know, you're 15 feet away. Okay? This is one type of lava flow, and in fact, this is the type of lava flow that produces all the rocks in Hawaii and all the rocks that cover the bottom of the ocean basins. So 70% of the surface of the Earth is covered by that, and we call that basalt. Okay? I have a sample of that basalt, which I'll just hold up now. This is actually, though, a sample of basalt from the bottom of the Pacific Ocean, 400 miles west of Mexico, where the Earth does some really interesting things. And I collected this sample on a trip that I took in 1997, where we actually dredged up material from the bottom of the ocean, beneath the water column. If you can see the shine off the top of that, that's glass, that's volcanic glass. So this is one type of volcanic eruption. Here's another. This is Stromboli, southern Italy. In essence, an almost identical composition of the lava that flows at Hawaii, but we call this fire fountaining. So in this case, I think everybody would agree that it's being brought out of the earth by some slightly different set of processes. Instead of being squeezed out of the toothpaste tube such that we have this nice quiescent flow across the surface, here what we see at Stromboli is that it's being, to some extent, violently ejected. And at night, it just makes for a spectacular visual. So that's the second way in which lava can be brought out to the surface of the earth. Then we go to Mount St. Helens. And I show Mount St. Helens because that's the year that I was in 6th grade. And so Mount St. Helens played heavily, even though we didn't have cable or CNN or Fox. But nonetheless, everybody knew Mount St. Helens erupted. And that's also the year, I'll tell you in a minute, I think that if I were to go back and say the first time I became interested in what you would broadly call volcanic processes, that's the year it happened, for a different set of reasons. But Mount St. Helens, here we're looking at it pre-eruption. Here we're looking at it during the eruption. And here we're looking at it after the eruption. And all I want to highlight is if you go from the top left to the center to the bottom right, notice all of that material. Okay? All of that material, that used to be within the earth. Okay? At some point in the geologic past, this particular area was flat. There was no Mount St. Helens. And over tens of millions of years, geologic processes took all of that material that we think of as lava from somewhere within the earth, miles to tens of miles beneath the surface, and it slowly burped that stuff up out onto the surface and created what we call Mount St. Helens. And in an instant during this volcanic eruption, notice how much of that mass is then moved. It's transferred. A significant amount of that mass is moved up into the atmosphere. Much of that mass was moved laterally, so Mount St. Helens is what we call a lateral flow, where all of that was moved out to the side. Now we're in the Caribbean. Soufriere Hills erupted, and what you can see on the left-hand side is sort of the pre-eruption, the pre-cataclysmic eruption cloud. And what you can see on the right is the main phase, the main eruption phase. On the right-hand side, two false color images that will sequence back and forth. And what you're looking at here are clouds. All of that white is clouds. And when the clouds disappear, you're looking at a later point in time. And all I want you to pay attention to is all of this material here. All of this light gray material that is lava or ash or magma that prior to the eruption was beneath the volcano, beneath the surface. Okay, so what do we have then? We have different ways in which we observe volcanoes erupt. We also observe that volcanoes erupt in different places around the world. So here I am in, I think this is 6th grade. That was the first year I can actually remember having to do what we would call library research. Okay? And in my middle school, we had a library, and there was a set of Britannica, Encyclopedia Britannica, and we did Roman history. I do recall that that was the first time I would have to go to the library, and I would have to read about all of the various things that happened during the Roman Empire, and this is termed the Garden of the Fugitives, and it's an image taken from Pompeii in southern Italy. And what you're looking at here are what had been casts of people. Okay, so what we now know is that Mount Vesuvius in southern Italy erupted in the year 79 of the current era. And as it erupted, the inhabitants of Pompeii were in essence blanketed with all of that ash that you could see in the previous images erupting from St. Helens and erupting from Soufriere Hills. The same thing happened at Vesuvius. All of that ash was blown out such that it moved south and southeast of the volcano and southwest of the volcano, and it moved through so quickly that you can see in some of these images, archaeologists and anthropologists look at an image like this of the person's arm covering their face, probably trying to shield themselves from the ash and from the heat. And what happens then is that once they're coated in that ash, the bodies are in essence decomposed. So when this was found, what they actually came across were hollow spaces in the ash. And if you pour plaster of Paris, or I'm guessing something like that, into that, you then create a cast. So what we're seeing here are people within minutes, tens of minutes, following the eruption of a major volcano less than 2,000 years ago. Okay? We're preserving that in time. And if I go back, I think for me that would probably have been the earliest fascination I can remember, because it was also the same year as Mount St. Helens. So you're thinking about, for me, wow, Mount St. Helens erupted, that's kind of cool. But then seeing images of this and saying, wow, that's really amazing that we can go backwards and put this story together. So here's Rome, here's Naples, and it sits just behind Naples. So here's the bay, we're looking at a portion of the city of Naples, and here's Vesuvius, taken in recent times. And here's another volcanic eruption taken in 1944. So something else that geologists and all people in society have observed is that volcanic eruptions are cyclic. Okay, Vesuvius, I showed you, produced the Garden of the Fugitives in '79. Here we have an eruption in 1944, and we know that Vesuvius will erupt again. So the city of Naples is in excess of 1 million people. So a lot of geologists concentrate a lot of their energy on trying to understand how and why and when volcanoes erupt, so that you can better develop forecasting techniques. Because the ultimate holy grail would be that somebody turns on CNN or Fox or Channel 7 and it says, we've just been warned that Friday at 7 o'clock Vesuvius is going to erupt. And you have several days to try and escape or move out of that area. We know a lot about the eruption of Vesuvius because of two characters. The first is called Pliny the Elder, and the second is Pliny the Younger, who was the nephew of Pliny the Elder. And Pliny the Elder was sort of a Roman statesman, and he had a house here at Mycenae, here. Vesuvius is here, and when Vesuvius erupted, it sent its ash out almost like a cone to the south. Pliny the Elder took his fleet of ships, and he sailed them across the Bay of Naples to try and rescue people. And while he was doing this, Pliny the Younger was 17 or 18 at the time, and 3 or 4 years after the eruption, he wrote a sequence of letters. This is one that he wrote to his friend Tacitus, who was also a high-ranking person in the Roman society, chronicling exactly what happened. And for geologists, this is great. Okay, this is in essence a blog from 2,000 years ago of somebody who witnessed Vesuvius erupting. And so we're able to take this and use this as one piece of evidence to better understand the cyclicity of how Vesuvius erupts. Are there changes when it erupts? Were there any warning signs when it erupts? Okay. We know now, here shaded in black, all of this is where the ash and lava from Vesuvius, all of that black area is where the ash and lava from Vesuvius were sort of thrown. Okay? And you can see the cities, among the ones that are more famous are Herculaneum here, directly southwest, and Pompeii here, directly southeast. And by studying these cities, and by looking at how quickly those lava flows and ash flows moved through those cities, it gives us some sort of sense of the timing that you have to try and escape one of these cataclysmic volcanic eruptions. But imagine that you wake up one day, and you go to the marketplace in Pompeii, and Vesuvius comes to life, and it sends up this phenomenal cloud of ash and volcanic debris. And you see this going up almost as if it's billowing from a chimney stack. And within seconds, all of this ash, which is in excess of 1,000 degrees centigrade, whooshes down the mountain straight into your city. You end up with the people that we see in the Garden of Fugitives trying to cover themselves because there is no escape. There's no way that you can get out of the path of that. A lot of these areas have been excavated. So today you can go and you can walk around these ancient cities and you can get an understanding of how close they are to Vesuvius. So let's move closer to today. Mount Pinatubo erupted in the early 90s. Mount Pinatubo is here in the Philippines, sits here just to the northwest of Manila, the capital of the Philippines. This is a photograph that I showed you in the first slide, taken from Clark Air Force Base. This is 3 days before the, quote, cataclysmic eruption. So it's in essence a small-scale precursor of what is to come in a few days. This has been studied intensely because in this volcanic ash, there also is a phenomenal amount of sulfur dioxide. So a number of people in our department here, as well as elsewhere around the world in geology departments, have focused on Mount Pinatubo because when it erupted, it emitted about 20 million tons of sulfur dioxide into the atmosphere. And one of the things we know from volcanic eruptions is that when they contribute significant quantities of SO2 into the atmosphere, that can play a role in modifying climate on an annual to multi-year scale. So what I show you here, the top is actually just a beautiful photograph taken by someone on the space shuttle. And what you're looking at are the top here, these really high cumulonimbus clouds. These are these tremendous thunderstorm squalls that we find in the Midwest. They extend up to about 40 to 50,000 feet above surface. And you're looking at 2 layers here of the aerosols from Pinatubo. So Pinatubo, which sits only a few thousand feet above sea level, when it erupted, all of that ash, or some significant proportion of that ash, got shot up into the upper atmosphere. And on the bottom of the screen, you're looking at images here, satellite images, and all I want you to notice is going from left to right as you increase the color from blues, pre-eruption. This is June 15th to July 15th, so this is the day of and a month following the eruption. Notice how quickly all of these aerosols emitted from Mount Pinatubo, they essentially encircle the Earth. They blanket the Earth. So something that we think of as being not in our backyard, oh, that's in the Philippines, that's on the other side of the Earth in the southern hemisphere, within days to weeks to months, we respond to Mount Pinatubo erupting. So it's important to understand volcanoes no matter where they are because we know that they can have very far-reaching effects. Top left here, these were airplane hangars, and the weight of all that ash has caused those airplane hangars to essentially crumble. And the bottom left here, what looks like snow, those are American vehicles on an American military base covered in volcanic ash. So a phenomenal amount of material that gets sent up and then rains back to the Earth. And then on the right-hand side here, in black, shows you simply the aerial extent of all the ash from Mount Pinatubo. Okay, so locally, the actual ash that we look at here and think of snow covered a significant amount of Southeast Asia. All right, so how do volcanoes work? Okay, everybody's got a good idea of what is a volcano. We have different types of volcano. We know that we have volcanoes in multiple places on the surface of the Earth. When you look at Pinatubo, I want you to think of it as follows. Okay, we're looking at all of this ash that's erupted here. All of that ash prior to the eruption, in the cartoon image on the right-hand side of your screen, sits in what you can think of as a big bathtub. But the bathtub is full of magma. And all magma is lava before lava erupts. I want you to notice, though, in this sort of artistic rendering, that this bathtub of magma is large. Okay? On average, when we experience or observe a volcanic eruption, only about 10 to 15% of the magma in the bathtub actually erupts to the surface. Okay? The majority of that magma remains beneath the surface, and eventually we can see it exposed in places like Yosemite, which I showed on the first slide. And then I want you to notice here, beneath the bathtub of magma, all of these what look like little veins that extend down to depth. What I want to walk you through now is sort of a basic understanding of how these magma bathtubs are formed and where are they sourced and what process is then responsible for having really quiet, easy eruptions like Hawaii versus really cataclysmic, destructive eruptions like Pinatubo and Mount St. Helens. So if you look at a map that shows you all the volcanoes active on the surface of the Earth, what do we see? We see volcanoes in places like Hawaii out here. We also see that there are volcanoes all along the Aleutian Islands in the North Pacific, Alaska. The entire west coast of North America is riddled with volcanoes. We move down then into Central America, lots of volcanoes. South America, lots and lots of volcanoes. We see the same thing here in the Afar Triangle in East Africa. Lots of volcanoes in this region. We see it here in Indonesia. Okay? the South Pacific, Japan, moving up towards Kamchatka, the arc off of eastern Russia. We also see lots of volcanoes, though, notice here, in the middle of the ocean basins. And it turns out that those were completely unknown until World War II. So World War II, what did America become very interested in? We became very interested in defining our surroundings. We thought we had a pretty good idea of our surroundings that were exposed on the surface of the Earth. But we then had submarines, and as those submarines were moving around the Pacific and moving around the Atlantic and trying to make sure that submarines from other countries weren't coming towards us, we started to use a new tool called sonar. And for geology, that was great, because there was a geologist named Harry Hess, who's shown here top left, who eventually rose to the rank of Rear Admiral. And he's shown here commanding his ship, his submarine, the USS Cape Johnston, in the Pacific in World War II. Now, Harry Hess was a professor of geology at Princeton University who enlisted in the Navy, who fought during World War II, okay, which is a completely new definition of a sabbatical. Okay? But when he was out there in his sub, he had access to sonar. Now, what is sonar? Sonar is nothing more than taking sound waves, and you essentially shoot them off the bottom of a ship, and when they hit the surface, the ground surface beneath the ocean, they ping and they get bounced back up to you. You continue to shoot them down, they ping and they get bounced back up. So imagine that you're moving almost like you're mowing a lawn. And as you move, you're shooting these sound waves down, and then you're receiving them as they come back up. Well, what does that do? Okay? What happens then is if you take all of those sound waves and put them back together, they map out the topography beneath your submarine. And prior to Harry Hess's trips into the Western Pacific, most scientists thought that the topography on the bottom of the oceans was flat. If you went to LA and you put on scuba gear and you started walking and you went down beneath the water, you would just be on a perfectly flat bottom and you would eventually come up in Asia. And the same thing would happen if you went from Washington, D.C. to Paris. You'd leave D.C., you'd put your super scuba gear on, you'd walk, you'd go under the water, and then boom, you'd come back up and there you would be in Paris. Okay? World War II totally changed our landscape, because Harry rode around the Western Pacific pinging everywhere he could go, and he put maps together that tell us that today it's a very different landscape at the bottom of the ocean than what we previously thought. What you're looking at here is something called a ridge or a rift. What Harry and others after him found is that the Earth, you can think of it as a baseball or a softball, how you have the seams, the threads around the baseball or the softball, is in essence covered by a rift or a ridge that extends 40,000 miles around the surface of the Earth. And it's shown here. So if I place us up here in Iceland, watch the pointer here, and I just want to trace this ridge in the Atlantic. It moves this way. And you notice the color change behind the pointer? Okay. Moves down to the southern Atlantic, moves over here to the Indian Ocean, up along Madagascar, moves down here and in this direction. We see the same thing in the Pacific. Totally changed geology, because all of a sudden it gave us an idea that not only was the bottom of the ocean not boring and flat, but it was volcanically alive. Since then, we now have been able to send submarines down with video cameras, and we have evidence from black smokers and white smokers that it is indeed really alive. We have places on the bottom of the ocean that are continually erupting lava and ash into the ocean water. Geologists since then have tried to put this all together, and it's shown here in a pretty good cartoon video. We call this mid-ocean spreading, okay, where those seams on the baseball are places where the Earth is cracked, and those cracks on either side are pulling away from each other, and as they're pulling away from each other, here to the right and here to the left, all of this former rock that exists is melting and being moved up towards the surface, something we call decompression melting, and I'll show you a demonstration in a minute to drive that home. So for geologists, this was truly a day of awakening, and for the next 30 to 40 years, all the journals have papers that went back and forth on whether you believe this or whether you didn't believe this. We've put that together today into a cartoon where that mid-ocean ridge spreading that I just showed you that happens out here generates what we call the ocean lithosphere, or the rock, the crust at the bottom of the ocean. And that crust at the bottom of the ocean moves, and as shown here, as it moves towards continents, one of the things that we observe is that that crust from the ocean sinks, the crust of the continents, in this case think of it as North America, rises, and it just so happens that volcanoes such as Mount St. Helens, such as Pinatubo, such as Soufriere Hills, such as Vesuvius, all of those volcanoes share the commonality that they sit almost exactly 100 kilometers or 62 miles above where this ocean plate is being underthrust beneath the continent. Okay? Where that occurs, we produce volcanoes. So this is another cartoon video, and it shows you now we have our ocean crust that used to be way out here, moving towards, let's say, North America. The ocean crust is really dense and it sinks. The continental crust is less dense, and so it, quote, floats. And when this occurs, we get magmas at 100 kilometers or 62 miles deep that then rise up towards the surface. Okay, so we've, in the last 2 generations of scientists, been able to take observations and move us light years into the future in terms of refining our understanding of these processes. And all I want to pause and highlight here is this red stuff is lava. Okay? All of this brown is rock. Okay? So you can think of it as the rock you might pick up or the rock on your granite countertop. What's happening here is that all of this rock created out at these mid-ocean ridges, what does it sit beneath? The ocean. What is the ocean? A huge supply of water. All of that water, okay, interacts with these rocks on timescales of tens of millions of years, and as that water is pulled beneath the continents here, you can almost imagine that it's an upward sprinkling of water into the mantle beneath the continent, and we produce that magma. Okay? Looks similar to the lava lamp that we have up here on the front table, and you can demonstrate the process with a coffee press. How many people in here like a French press coffee? Okay, a lot of hands. What happens in a French press coffee? Similar to what I've got shown here. Okay? In this case, instead of coffee, we have sponges and we have water. Now, when you make coffee, what do? You fill it with coffee, you fill it with hot water, you wait for the coffee and the water to come to some sort of equilibrium, you push the French press down, you separate the grinds from the water, and you drink the water. The same thing happens beneath volcanoes such as Mount St. Helens and Vesuvius. Geology took what had been all rock, it put in a little bit of water, which causes some of that rock to melt, and as that happens, geology separates the remaining rock from the water, and that new water now, what does it do? Where does it go? Which direction? Up. It moves up. Same thing happens under volcanoes. Okay? We call this partial melting, where you took 100% rock, you partially melted it, and then some of that melt rises ultimately to become volcanoes. You can see the same thing with a lava lamp. We've got red and we've got yellow. Red is more dense, yellow is less dense. So the red, being more dense, should sink. But what happens when the red sits on the bottom, it's doing what? It's absorbing heat. And so it sort of simulates this process that happens under volcanoes like Mount St. Helens. In this case, that red, you can think of it as the partial melt. Okay? Where in nature, we put a little bit of water into the material down here, we melt a little bit of that rock, and we now have this new liquid that rises. And as it rises, it reaches the surface, and it either reaches the surface as a nice quiescent basaltic lava flow in Hawaii, or it can reach the surface for reasons I'll talk about in a minute and explode like Mount St. Helens. I want you now to think of this cartoon and this distance of 100 kilometers or 62 miles. And imagine now we've got this magma down here. That magma has some water in it. That magma has some CO2 in it. And as a segue to the future, that magma also has every other element in the periodic table, including gold and copper and platinum and silver. And what happens is that as that magma rises, its ability to keep all of that water dissolved in it decreases. Okay, so as that magma moves towards the surface, what you're seeing here shown as blue spheres is that the water in these blue spheres that down here at 60 miles was dissolved in that liquid. As that magma moves up towards the surface, it can no longer contain all of that water, so that water slowly comes out of the magma as its own phase, its own entity. Okay? It forms little bubbles. Now, how many people in here have ever blown bubbles at a birthday party? I should have brought this. What happens? You blow and bubbles form. Think of it here as happening naturally, where those bubbles that you blow are originally dissolved in the magma at some depth beneath a volcano. And as the magma moves up towards the surface, those bubbles are blown. Okay? We know this happens because lots of rocks that erupt at volcanoes have textures consistent with gas, bubbles, having been in that magma before that magma erupted. So the image on your left is what we call vesicular basalt, and the image on your right is pumice. And if you look at the vesicular basalt, you can see how spherical each one of these holes are. All of those spherical voids had previously been bubbles, and they were filled with a fluid that was a mixture of water and carbon dioxide. So we now know that water and carbon dioxide that resulted in the formation of these spherical voids at some high temperature and pressure within the Earth, those bubbles were dissolved in this rock when this rock was a magma. Okay? And we can demonstrate that. It's something geologists call reduced pressure boiling. So what do we have here? We've got a flask, and the flask has water in it. Okay? Now, as the flask sits here, there also is a column of air that sits above the water, and that air is at atmospheric pressure. Inside that water is also dissolved air or dissolved gas. What do you think happens if you reduce the pressure, this column of air, on the water down here? I'm going to connect this up to a vacuum pump where we're going to suck out the air from above, and what do you see happen at the bottom? You form bubbles. Okay? This is a very simplified model that describes, I think, or illustrates really well exactly how we think bubbles can form as those magmas 60 miles beneath Mount St. Helens slowly move their way up towards the surface. All of that water, all of that CO2, all of that gas that used to be dissolved inside the liquid, as that magma moves up towards the surface, the pressure on top of the magma is reduced. And as you reduce the pressure on the top of the magma, it can no longer contain all of that gas, and so it releases that gas. It boils. So the same type of boiling that happens here, similar to boiling of water at home when you make pasta, okay, when you reduce that column of pressure, we get these bubbles. And the bubbles, it turns out, are extremely important at controlling what type of volcanic eruption we observe on the surface of the Earth, as well as another property of this liquid that we'll talk about in a minute. So what happens now if I turn this off? We let the air back in, the boiling stops. Okay, so we call this reduced pressure boiling, and it's extremely important at determining the style of a volcanic eruption on the surface of the Earth, and it turns out it's also extremely important at controlling which types of volcanoes yield ore deposits. You can stand here and you can watch this eruption. Okay, that's an eruption. Just like St. Helens, it's an eruption. We now have a lava flow, okay, nice and quiescent. If you go to St. Helens, it's really different. Okay? And there were a few people affected, a few fatalities when Mount St. Helens erupted. I don't think anybody, if they were on the flanks of Mount St. Helens and somebody came up to you with a park ranger shirt on and said, you know, Mr. and Mrs. So-and-so, we predict an eruption in 3 hours, we advise you to leave, you would say, oh, that's okay. You know, we've been to Hawaii, it's not a big deal. Everybody would leave because you see how much material comes out of the top of Mount St. Helens, and you know that some significant amount of that material is going to move down the sides of the volcano. So you get out. So then what causes the difference between the eruptability or the style of eruption of Hawaii versus the style of eruption at Mount St. Helens? Okay? The same process that we just talked about here, this reduced boiling, happens in both locations. It turns out that one of the reasons that you have very different eruption styles at St. Helens versus Hawaii has to do with the viscosity of the magma. Now, viscosity is a new word I haven't used yet today. And all viscosity is a term used to describe resistance to flow. Okay? How many people in here drink tea? How many people in here who drink tea like to put honey in their tea? Okay? When you take honey out, how many people notice a difference in how quickly the honey moves off their spoon when you take honey out in the middle of July versus honey out in the middle of January? In January, the honey is more viscous. It resists flow because it's colder. The same thing happens to magmas in the real world. If we take a basalt and we take a granite, so here is a granite countertop, and here is a basalt. This is roughly the composition of what erupted from Mount St. Helens, and this is exactly the composition of what erupts at Hawaii, almost exactly. Okay, both of these are formed from magmas at some number of miles beneath the surface of the Earth. Both of these contain water and CO2 and other elements that behave better in a gas when the magmas experience reduced boiling. So what does that mean? Well, there's a really simple demonstration up front that can give you an idea of viscosity. Each of these liquids are in here because they have a different density, and each of them have a different density, have a different viscosity. And we can watch what that means. But before we watch it, I want you to think about the bubbles that rose in this demonstration. Okay? So now we want to watch it. Okay, here's what I want you to do. Okay? Up here, we've got a magnet on the outside, and we've got a steel sphere on the inside. Steel, I'm guessing? Good enough. When he removes the magnet, that steel sphere is going to go which way? Down. That steel sphere is going to go down, but what do we predict has to happen when it goes down and hits this first liquid? It's going to slow down. Okay? Because here we've got air and here we've got a liquid, and we know that any object is going to travel faster in air than it does in a liquid. I want you to pay attention to it traveling through this upper liquid, and then I want you to make sure you watch what happens when it moves into this central liquid. Pull the magnet off. You just have to bend it down. What happened? Slowed way down, right? I mean, that's like you're doing 90 on the highway and you see a cop a mile ahead. What do? Slam on the brakes. You slow way down. Now what's going to happen? It's at the bottom. Let's do it again. We move it back up to the top. And I want you now, you've seen it slow down significantly when it goes from the top liquid to the middle liquid. Now I want you to pay attention to this bottom layer and see what happens. So it's going pretty slow. What happened? It sped up. Okay? So what are we looking at here? We're looking at a steel sphere moving through 3 liquids, and each of those liquids have a different viscosity. The same thing happens beneath volcanoes, where we have, instead of a steel sphere dropping down, we have bubbles moving up. So do this mental exercise now. Imagine that, thank you very much. Imagine that this is a bubble moving up. Okay? What happens when that bubble hits this liquid barrier? The bubble, it's slowing down. Its ability to move is now retarded. Okay? It's harder for that bubble to move up because the viscosity of this liquid is higher than the liquid at the bottom. What happens now when I cross this boundary? It can move more easily. So it turns out, in nature, if we think of magmas like Hawaii and magmas like Mount St. Helens, that the viscosity of the magmas beneath Mount St. Helens are high, And the viscosity of the magmas beneath Hawaii are low relative to one another, so that as each of those magmas rises from what could be the same depth beneath the volcano, the bubbles under Mount St. Helens have a hard time escaping, okay? Just like the bubbles that would move through this central liquid. But the bubbles in the magma moving under Hawaii, because it has such a lower viscosity, they escape nice and easily. So we know what volcanoes do. We kind of know why they erupt. We've talked about this reduced pressure boiling, viscosity, basalt at Hawaii versus granite-type magma at Mount St. Helens. Here's another map. Same continents, same Earth, same oceans. But all I want to highlight is, and I'm going to go back and forth for a couple of slides. Notice all the volcanoes. All of these dots here are major ore deposits for metals such as copper, gold, platinum, silver. Notice the volcanoes, notice the ore deposits. Volcanoes, ore deposits. A lot of overlap. The whole western margin of North America and South America, lots of volcanoes, quite a few ore deposits. Indonesia, lots of volcanoes, lots of ore deposits. Japan, volcanoes, ore deposits. Kamchatka, volcanoes, ore deposits. So an observation that Earth scientists have made for hundreds of years is that where you do see volcanoes, you do commonly observe ore deposits. The Romans did this. The Greeks did this. The Egyptians did this. They knew that they could go to certain areas, and in the same areas where they could see sulfur gases coming out of volcanic terrain, they also could find concentrations of gold. Okay? So this is nothing shockingly new. But what I'm interested in really doing now is saying, okay, we think we know how volcanoes form, and we think we know why volcanoes in a place like Hawaii behave they do versus volcanoes in a place like Mount St. Helens behave the way they do versus volcanoes at Mount Fuji behave the way they do. Well, lo and behold, whoa, if you then plot up all the ore deposits, there are a lot of ore deposits associated with areas that are volcanically active. So maybe we can take the knowledge that we have from understanding how volcanoes behave and use that to understand how these ore deposits form. It turns out that ore deposits related to volcanoes supply a lot of metals that we use every day. And here I just highlight 4 of them. Okay, about 70% copper, 54% gold, 60% silver, and 99% molybdenum. And if you haven't heard of molybdenum, it's heard of you. You have already used it today, you're going to use it tonight, you're going to use it tomorrow, you're going to use it next week. It is in a variety of materials that enable us to do everything we do on a daily basis. From airplanes to cars to structural support to reinforced concrete, it's around us. So why is it then that these metal deposits associated with the volcanoes we've already talked about, why are they observed forming together? We all use these, okay? Here's a slide, and all of the pictures are things that I use all the time. I love donuts just like everybody in the room. I love to bike. Okay, when I go to the gym, and I have power delivered to it. When I woke up this morning, I turned the light switch on. It turned on the HVAC system in the house. I drove here. I have a cell phone like everyone else. Turns out cell phones have about 0.003 grams of gold. And I love taking work-related vacations. Okay, best perk of being a college professor who works on volcanoes, there are none in Michigan. Okay? So we all use this. Okay? Now, I lived for 7 years in the state of Nevada, where our budget was cut every year. So on the weekends, my daughter and I would go out and pan for gold. That's how we spent our time. She's panning for gold outside of Salt Lake City in Utah, which is historically what we did to find gold deposits. We would find the metals, and we would figure out ways to use them. So on the bottom here, okay, are I think the only numbers in the whole presentation. And all I want to highlight for these metals, which are among my favorite, is that in the crust, in that granite, in that basalt, in your soil, in your backyard, there's very little of each of these metals. The ppm stands for parts per million, and the ppb stands for parts per billion. So if you have 1 billion Hawaiis, okay, you would have 0.8, you would have 1.3 golds, okay? So what I want you to think of is that the average concentration of these metals is really, 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 really low. Okay? In order for any company to find a portion of the earth and to want to mine those metals from that portion of the earth, they work with something called a mineable or exploitable grade. And that's the concentration where it's economically feasible to go out and physically pick up that rock and separate the gold from the rock and then move that gold along in the supply chain. And all I want to highlight is notice the numbers change significantly. We go from 27 parts per million to 0.2 weight percent, 1.3 parts per billion to 2 parts per million. So we're talking about changing by several orders of magnitude how much metal we used to have as background to how much metal we need to mine. That's what's given over here. Okay, this is how much you need to increase the concentration of any of these metals to make it economically feasible to mine them. And here's our global annual demand. This is 2011. Now you look at those numbers, 25 million tons of copper metal, 4,000 tons of gold. Okay, so society has established a demand for all of these metals. And I'm interested in trying to understand how we can better predict new sources of these metals to supply society's demand. So one of the areas that I'm fascinated with is shown here. So here we have the US, here we've got Utah, here we've got Salt Lake City, and near Salt Lake City, just to the southwest of Salt Lake City, is an area called Bingham Canyon. It's a fantastic, in my opinion, example of a place where nature has taken some rock somewhere in the earth with some really low concentrations of metals, super amplified those concentrations of metals, and then just dumped them all out in a teeny tiny portion of the Earth's crust, where we can go out, and I say the collective we can go out and we can mine them for use. Here's what that mine looks like. It is the largest man-made hole on the surface of the Earth. 4,000 meters rim to rim, 1,200 meters bottom to top. Here's Ann Arbor. Now this red line here is 1 kilometer. So if you walk from Main Street over here and you walk towards, that's Glen, that's a kilometer. Okay? So that distance times 4 is the Bingham Canyon porphyry deposit. It's huge. It's huge because this is how much metal it contains. 22 million tons of copper, 23 million ounces of gold, 190 million ounces of silver, 850 million pounds of molybdenum, and 1 billion tons of sulfur. That is a phenomenal quantity of metals. Okay? They truck it out from the bottom to the top on trucks that you can barely see. Here's 1, here's 2, here's 3, here's 4, that carry 400 tons of material at a time. And here's a tire, okay, with my wife and children for scale. Okay, this is a massive enterprise. But notice the amount of metal that it contains. It was the first of this type of ore deposit ever to be mined commercially beginning in the 1890s. It's huge for the economy there. Okay? In my house, among our favorite sports is soccer. The company that is the principal for Bingham Canyon is Rio Tinto. They sponsor Real Salt Lake, which has had its ups and downs, but has historically been among the best of the Major League Soccer teams in the US. That mine supplied all the metals for the Winter Games held there in 2002. All the metals, okay, came locally, which means you wear metals that are LEED certified. Just as a fact that nobody in here may have known, if you take all the gold ever mined, ever, in the history of the world, it would fill that soccer field to a depth of 2 meters, which is roughly about what I am. Okay? That seems like a lot of gold. Gold is a metal that we use the term malleable to describe. It's extremely malleable. You can take a hammer and you can hit it and hit it and hit it and hit it and hit it, and it just gets flatter and flatter and flatter and flatter. So a little gold goes a long way. But the demand for gold grows. So if we think of Bingham Canyon, this deposit where we mine lots of gold and copper and silver and molybdenum and other metals, today it obviously isn't covered by a volcano, but it was when it formed. So about 35 million years ago, that area just to the southwest of Salt Lake City, before the big lake was even there, had volcanoes that were there, and those volcanoes were erupting. And this was actually the study, the focus of a PhD dissertation by a former professor, Professor Emeritus Steve Kessler. One of his students, Dan Core, from our own university here, studied this and graduated in 2005. So we have the Bingham Canyon mine today. 35 million years ago, there were volcanoes above it, and those volcanoes were probably 2 to 3 miles above this portion of the Earth's crust or rock that today is exposed. So in 40 million years, those volcanoes have all been eroded away. Okay? And there are a variety of reasons we know that's happened that I can tell you about after the talk. So if we think we understand Bingham Canyon, and we understand that it had volcanoes above it, and we think we understand how volcanoes form, we think that this reduced pressure boiling is important. If we think we understand that we have ocean crust made out here, and that ocean crust moves and it gets pushed or subducted underneath the continents, the model is that as that ocean crust sort of wets or sprinkles the mantle, here's what the rocks down here at 60 miles look like. All of these bright spots are minerals that we call sulfides. Okay? There's sulfur as an anion, and then they have various metals such as iron, copper, nickel, silver as the cation. Put those two together and they make a sulfide. They hang out down here, they're perfectly fine, until this process out here hydrates them. These continents and these ocean rocks are moving, so what happens is all of these little minerals, they now become melt. They become a liquid. And as everything is moving around down there, that liquid is what escapes. So that French press thing that I did over here, I'm now going to try and simulate what happens in the case where instead of it just being a liquid and that liquid is filter pressed or moved up, now what we have is a fish tank. We've got different colored golf balls. Think of those golf balls as part of the rock that sits 60 miles beneath Mount St. Helens. Also sprinkled in here are sugar cubes. And those sugar cubes on some of their faces have red food coloring. Think of that red food coloring as gold or copper or silver. Okay? So imagine now, this is what's happening 60 miles beneath Mount St. Helens. As we wet all of that rock, we're producing a liquid. We're partially melting that rock, and that liquid is going to move up.
It's turning red.
Okay? It's turning red, which means what? That the gold and copper and silver that used to be on the sugar cube, that used to be part of the rock, those metals are now dissolving in the liquid. They're becoming part of that liquid. So it's a process that you can think of as transferring material from a rock. Now that material's in the liquid, and I previously said that that liquid moves which way? Up towards the surface. So what we're looking at here with the red water is what we think is happening at depth beneath places such as Bingham Canyon, Mount St. Helens, Mount Pinatubo. That all of that material is rising up towards the surface. So here's what I want you to have taken away now, all right? All volcanoes come from magmas. Different magmas have different viscosities. All of those magmas have gas dissolved in them. And as those magmas rise up towards the surface, if a magma has high viscosity, those gas bubbles, they rise slowly. Okay? It's hard for them to escape, like our little demonstration we did here. If those magmas have really low viscosity, those bubbles can move really quickly. So at a place like Hawaii, when that basalt moves out onto the surface, any of the gas that was dissolved in it, it's easy to get out. It just moves. At a place like Mount St. Helens, or the volcanoes that sat beneath the Bingham Canyon deposit near Salt Lake City 35 million years ago, those magmas are really viscous. And so those bubbles have a really hard time getting out. Okay? Ultimately, what happens is that in those viscous magmas, those bubbles, just like our red food coloring here, they suck in all the metal, gold, copper, silver. They rise, and as they get up towards the top of the magma, it's really hard for them to escape. And so they develop a lot of pressure, and they eventually have a high enough amount of pressure within the bubble that it literally erupts that magma chamber in the same way I described a volcano forming. But in this case, the pressure change when those bubbles escape the magma chamber is so significant that all of those metals, as they are in the bubbles that leave the magma chamber, instantaneously, because of that pressure drop, they leave the magma chamber and then they precipitate out. And when they do that, they form ore deposits like Bingham Canyon. Now, it turns out if you look at that global map of volcanoes, the rule of thumb is that for, let's say, 1,000 volcanoes, you might only have 10 where an ore deposit formed. So it's a needle in a haystack. The saying is, all the easy ones have been found. So we found those 10. But we know, or we think we know, that because we understand really well how all 1,000 volcanoes form and how all 10 of those, quote, easy to find ore deposits form, what I'm interested in doing is figuring out if we can come up with models that predict where the harder ones are. Okay? Because we know that the demand for those metals is only going up. It's got a really positive slope. So if we know demand goes up, there's a craving that drives supply to meet that demand. And so I'm interested in understanding 1,000 volcanoes, 10 ore deposits, where's the next one? How do we find it? How do we take all of our collective knowledge, put that together, crank out a model, and say, okay, here's where you should go look. And one of the things that drives me is that I think we can do that looking in a much better, much more sustainable way than we previously did. We can minimize the environmental footprint so that when we go in and we do, quote, exploration geology, we can do it with a clear conscience. We can go in there and we can work with all parties to make sure that any mining that's going to be done is done such that that footprint that's going to be left behind is as small as possible. Here's a pretty good simple demonstration of how volcanoes erupt. And what you see simulates, I think, really well the ash that comes out of volcanoes like St. Helens and Soufriere Hills and Vesuvius. And I pointed out with one picture from the space shuttle that the aerosols from Mount Pinatubo erupted at only a few thousand feet above sea level. Those aerosols made it up to 50,000 feet above sea level. So what we have here is a Diet Coke. Okay? Geologists like to stay slim and trim. It's a Diet Coke. What does a Diet Coke have in it?
Carbon dioxide.
CO2, carbon dioxide, bubbles. So we have a magma. And what we're going to simulate is how those bubbles, if they are instantaneously released, and the key word here is instantaneously released, what do we predict would happen? Now, it should be obvious based on the fact that this is here, okay, and how high it extends, what may happen. In this case, we use Mentos, and Mentos, if you look at them under the microscope, are like golf balls. Okay? Golf balls have lots of divots in them. Champagne glasses now are laser etched to have divots in them. So when you drop the Mentos, those divots act as little nucleation sites for carbon dioxide. So the more divots, the more nucleation of carbon dioxide bubbles, the more explosive the eruption. Same thing happens in the real world. Okay? The more gas and the more bubbles that nucleate in any given magma chamber, the more explosive the eruption. All right, so you're going to hold this. No, don't pull yet, don't pull yet. Okay. So we're going to do a countdown. So you're going to count down backwards.
We're going to have you stand right here.
Okay. Did your parents sign the liability release form?
And then pull it straight up.
Okay. And I just want you to pull it straight back. Okay, so count it down.
Whoa! Mentos and soda fountain.
Okay.
Wow.
Now that is, thank you very much.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.